This is a 20 millimeter steel plate, thick enough to stop a bullet, and a beam of light is about to cut through it like a hot knife through butter at 8 meters a minute. Here's exactly how that works. A fiber laser doesn't start with a beam. It starts with a diode. Hundreds of small semiconductor diodes, each one pumping light into a glass fiber thinner than a human hair. That fiber is doped with a rare earth element called ytterbium. When the diode light hits those ytterbium atoms, they absorb the energy, then release it again as photons at 1.07 micrometers. Every photon release triggers the next. That's the amplification, and it's where the light goes from ordinary to violent. The result is a beam with a wavelength 10 times shorter than an old CO2 laser. And wavelength is everything, because metal absorbs short wavelengths far more readily than long ones. Same power, but far more of it actually lands in the steel instead of bouncing off. The beam travels through fiber optic cable to the cutting head. No mirrors, no alignment. Nothing to knock out of true when a forklift bumps the machine. Inside the head, a collimator straightens the beam, then a focusing lens squeezes it down to a spot around 1/10 of a millimeter across. Now do the math. Take 6 kilowatts of power and concentrate it into a spot that small, and you're looking at millions of watts per square centimeter. The steel doesn't get hot. It vaporizes instantly. But vaporizing the metal is only half the job. The molten material has to get out of the way, and that's what the assist gas does. Nitrogen blows the melt out the bottom of the cut and shields the edge from oxygen, giving you a clean, bright, weld-ready surface. Oxygen does the opposite. It reacts with the steel and actually adds energy to the cut, letting you go thicker and faster at the cost of an oxidized edge. So why is CO2 finished? 3 reasons. Electrical efficiency. A fiber laser turns about 30% of its input power into beam. A CO2 laser manages 10, so you pay for the difference in electricity every single hour. Running costs, no laser gas, no mirrors, no resonator rebuilds. And speed on thin sheet, where fiber is 3 to 5 times quicker. There is a catch. That short wavelength reflects unpredictably off copper and brass, which used to destroy laser sources. Modern generators have back reflection protection built in, so it's manageable, but it's the one place where fiber demanded engineering rather than just winning outright. And this is the part most people miss. Once the beam came out of a fiber instead of a box of mirrors, the machine stopped being fragile. That's what unlocked 24-hour lights-out cutting, automated load and unload towers, and coil-fed lines that never stop. The beam got better, but the real revolution was that it finally became reliable enough to leave running overnight. Light amplified in glass, focused to 1/10 of a millimeter, and cleared out with a jet of gas. That's how you cut 20-millimeter steel with a beam. If you want more of this, subscribe. Next up, why press brake tonnage is the number everyone gets wrong.